Good afternoon and welcome to another ODS Videos webinar. My name is Mark Richardson. I'm the Marketing Manager with Vibrant Technology. I am joined again by our friend and colleague Dan Ambre from Full Spectrum Diagnostics, and we have a good one for you today. Title of today's webinar is Accuracy and Repeatability, and we all know that MEscope is the only ODS software that can process both video and accelerometer data. So we decided let's put it to the test. Let's do a real world test and see how data from a high-speed video compares with accelerometer and with the cell phone data. So Dan did some real world data collection, and we are going to take a look at all of that data today and see how things see how it turned out. Couple of housekeeping notes before we get going here. We are recording this webinar, so we'll get a recording posted up on our YouTube page here, probably a first part of next week. You can find our YouTube page at youtube.com/Vibrant Technology, and there you can see all of our webinar recordings from going back many years. There's also a number of training videos, both for MEscope and MEscope ODS videos. What else? If you got questions, hopefully we're going to have time for questions. We got a full hour of information to provide, so I'm hoping we'll have a little bit of time at the tail end of the webinar today to get to your questions. If you do have questions, feel free to type your questions into the dialog box there in the GoToWebinar panel on the right side of your screen. And we hope to get all your questions answered, because I know we're going to have a lot of them after this webinar. With that, let me hand things over to Dan, and we will get going.
All right, thanks, Mark. Welcome to everybody that's showed up today. Hopefully, after that big build-up, we actually do have a good webinar. It's a topic that a lot of people are real concerned about, and it's kind of strange. You know, I think it's a visual format, so it's more of subtleties of the animation for me instead of what the exact value of velocity or acceleration or displacement. But regardless, we're going to look at that. And Mark said this is a real-world application. This is a series of cooling towers in a power plant close to me in Minnesota. And I took data on all 13 in this case, and took multiple sets of data, different directions. So it was a pretty vast amount of data when it all got down to it, but found some interesting things. So MEscope ODS videos, high-speed video vibration analysis. The clip is processed with something called an optical flow algorithm. It enhances the subtle displacements at the pixel level. And rescales the amplitudes. It allows us to process the data and see what our human eyes can't actually see. And usually it's because the vibration is too small to see, but also if the event is too fast, we can slow it down with the high-speed camera. So there's a lot of functionality, a lot of different things that you can do, and we'll get into that a little bit as well. But the webinar here is a study in accuracy and repeatability, as we try to understand the difference in vibration levels captured by video and captured by traditional accelerometers. And there's a few things that I just found today that were odd, and we'll get into some of that. We're going to expand on signal processing while we're performing video analysis. This is important because of the time constraints. So we're going to see what is the optimum time to get a good animation, to get a good spectrum, and to get a good waveform. Okay, and there's a bit of resolution changes that will help us out on that. So we'll get started. Uh-oh, screen's locked. There we go. This is the inside of the turbo or of the cooling tower. If you haven't seen one before, the little cartoon I have at the bottom of the screen, there's a motor that's outside the cowling or the fan stack or what have you, you want to call it. There's two couplings. It's a long drive shaft. So there's a coupling at the motor end and a coupling at the gearbox end. The shaft goes into, the drive shaft goes into the right angle gearbox, and it's geared down, in this case, 13-to-1. And so our low speed shaft is powering this fan inside here. So the blade count is 7. I have some of the particulars up here. Our motor speed is 1780. The gearbox output speed with the 13-to-1 ratio is about 137. There's 7 blades, so we're going to have a blade pass frequency, a big one, actually. And we get multiples of that. And it really shows up in the spectrum of the videos analysis, because it's in the background, it's everywhere. It's in the deck, it's in the machine that's driving it, and it's also in that fan cowling that is deforming and fluttering. So there is a big pulsation from the inside. We're doing 2 different things for this webinar. We're going to do cell phone video, and I have an iPhone, so mine's set at 1080p slow-mo at the maximum frames per second I can get on my phone is 240. I believe Androids and LGs and all that have similar slow motion modes and high speed, usually used for slow motion. That should work as well for this analysis. Okay, I think we're also the only ones that can pull in cell phone data and do that, as well as high speed video. I have a high speed video camera. It's a Kronos 1.4. It has a frame rate at 1057. I mean, it can go really high, but you lose resolution. So the most optimum speed or frame rate is 1057 in this case. Anywhere close to 1000 is pretty fast. Okay, so inside, I was actually out there last week, and the door was open and somebody was working on it, and they laid some plywood down so nobody falls through this thing and hurts themselves. But this is the gearbox, the right angle gearbox. It's a little messy on the inside, a little moldy. But there's also I-beam frames that crisscross in here and hold the structure together. Some of it is wood beams, some of it is aluminum beams like you're seeing here, and that supports the gearbox structure and the fan structure. Okay, and we'll see some of that. I just worked on the motors, so usually you can't get inside. There might be wireless transducers that you can put on your gearbox to keep tally of what's going on day to day. The cooling tower, a little definition, is a specialized heat exchanger in which air and water are brought into direct contact with each other in order to reduce the water's temperature. As this occurs, a small volume of water is evaporated, reducing the temperature of the water being circulated through the tower. The fan up in the fan stack functions to suck air through the sides of the building. And the building that I was on, this is like a 5-story building with slats in the side walls, and it allows it to suck air in that's being forced in by the induced by the fan, and the water shower in there is designed to reduce heat. So it's a big specialized heat exchanger. The topics we're going to talk about are repeatability and accuracy. So repeatability is a closeness of agreement between independent test results obtained with the same method, same test material, same lab, same operator, same equipment. Now, if you're a guy that goes around and takes monthly readings, you know what this is like. If somebody takes over your route, they do things a little differently. And if you're not doing things the same, your data goes into alarm or changes and you're not sure why it did that. I've had cases where I've used a different transducer because somebody was using all the ones I planned on using, and the difference in the transducer caused such a change in amplitude that you wouldn't think it would, but it went through a bunch of stuff into alarm. So repeatability, a closeness of agreement between independent test results, okay? Accuracy is a closeness of measured value to a standard or known value. We're going to use our accelerometer, okay? In this case, the known values, there's 2 of them, would be the accelerometer measurements, and we took X, Y, and Z measurements on each of the motor housings on the outboard end. And the other control value that we're going to look at today is 1787. That's the speed of the motor, the rotating speed of the shaft. Why is that important? Well, there's a lot of peaks in the spectrum, and you can get caught up with, you know, the blade pass and the multiples of blade pass and all the different frequencies that might be there. This is a constant frequency that's in all the data because it's the turning speed. Might not be the biggest peak, but it's very repeatable, okay? So in our table here, and until this morning, I had a whole bunch of data and I hadn't formulated into a table, but it seems to work. I needed a graph in here so that I could better convey what was going on. So what you see here to the left is the cooling tower number. There were 13 of them. I took some partial data and I had to go back for the accelerometer data on a couple of them. When I got there, units 1 and 2 were under maintenance. And so I started with 3 and went up to 10, and then I broke my cable on my transducer, my accelerometer. And that kind of set me back. I didn't have a spare cable, and I couldn't fix it in the field. I ended up taking the data, but only 2 of the 3 channels gave me a good result. So I have, at least I have 8 different machines that I worked on. So X, Y, and Z measurements, these are all in inches per second. The raw data that we process will be in units of displacement. The reason I use velocity, inches per second, is because it's a lot easier. The displacement is a function of frequency. So if you change your frequency, you have to recalculate whether the machine is in alarm or not. If you use velocity, you just have to remember 0.3 inches per second. Typically, that's where the amplitude level where things start to change and some faults start to develop. Okay, for this long shaft cooling tower, 0.3 inches per second is a little low. There's a little more flexibility in the system, and usually 0.5 inches per second is used because we're going to have a blade pass frequency pulsation in there. Okay, regardless, I took this data and I plotted it against my cell phone close-up X, Y, and Z view, my high-speed camera close-up X, Y, and Z view. And you'll notice there's a couple columns that are blank. This analysis is two-dimensional. We're trying to do a two-dimensional video frame, basically a picture, and make a 3D representation. So in the case of this, you're going to have to take a couple directions. And I did do that. I have all kinds of data that I took. This was the best data for looking for the cell phone, the close-up images to see, or not the cell phone, the accelerometer to see how well it matched in the video, the representation of the transducer on the housing. Now, what I would recommend, if you're out there and you've wondered about this and you wonder what the precision, the repeatability, the accuracy, put a transducer on there. If you have walk around data collection, you can put a transducer on your machine, take the data, and then go take a video and leave the transducer on there. Now you have a reference point, and you can put a pixel on the screen, or you select a pixel on the screen that's on the transducer, and it should give you an amplitude in 2 different directions that are close to what you've measured, okay? And we'll show you how I did it, and you can improve on the process if you want and let me know about it, but that's what we're gonna do. So down at the bottom here, I have accelerometers in the X, Y, and Z direction. That would be the black, the green, and the red trend lines down here. And then I have, in the X direction, I have triangles. And those triangles tend to follow the response, okay? And that's what I was looking for. I was not comparing one to the other, comparing all the multiple parameters. I was comparing the trends, because even though you, like somebody else takes over your route for a week because you're on vacation and they put the transducer on the machine, but not in the spot you usually put it on because they don't know, the trends get screwed up. Same sort of thing can happen here in that if I select a point on the housing that I would normally put the transducer in, that should match the data from the transducer. And I tried to make that happen, and it's close. As you can see through here, all these triangles line up with the axial direction. The circles line up with the Z direction, and the Y direction is in green. Okay, so based on this, you know, I could crunch the numbers forever and can't tell you why they're different, but they're very close. And what we're looking for in accuracy is a closeness of a measured value to a standard or known value. Okay, and when it all boils down to it, we're looking at the motion. We're actually trying to see where the vibration problem is. And one of the unique things that we have in our software is we can overlay color contours and color scales, and we can see from that some very interesting things we're going to talk about in a second. My measurement conditions were arguably the worst possible combination, and my little quip is it's the worst possible day, but that isn't true. If it was snowing up there and it was all icy, and that would be the worst possible day. But out there, nice day, bright, sunny. We had wind gusts up 25 to 30 miles an hour, which normally wouldn't be a big deal if we were inside a building, but out here in open in the elements, 5 stories high, there was a wind tunnel effect around each one of these towers. You can see how they're kind of hourglass shape. The wind was blowing through there, and it'll do what wind does. It started moving my tripod. So even if I hold it down, the wind was buffeting my tripod, which means I have background noise from more than one source. The background noise from the wind was something that I'd never seen before or thought about adding to the background. The other background was from the motor and fan vibration itself. The deck was vibrating. There was blade pass pulsations in the fan stacks, and the camera and tripod were jittering all over the place. Okay. But we're lucky. We have some software advantages. We can take care of that and pull that background noise out, and I'll show you how we've done that. And as I mentioned, we have video data collection in multiple directions, and we're doing it with 2 different types of camera, the cell phone camera and the high-speed video camera. The cell phone camera had some issues in that it wouldn't get the higher order blade pass frequency numbers out of it. I could get, I think 1,000 CPM was the first blade pass frequency, so I could get a few of those showing up in my spectrum, but 120 hertz is where the data wandered off. Okay, so our maximum for 240 frames per second, our maximum frequency range is 120 hertz or 7,200 CPM for the cell phone camera. For the high-speed video camera, we can go much higher. We can go out to 30,000 CPM or 500 hertz and really see what's going on in the high frequency end. Okay, so a little problem as far as frequency range with the cell phone camera, but it also has a really nice color response to it, even indoors. And there's pluses and minuses. If I had my choice, I already have a cell phone camera. I'd get the software, play with the cell phone camera, see what the limitations are, and then on those problems, go get the high-speed camera later and start working on that. But it's a great combination for vibration analysis, and you'll see things you've never seen before. And it seems like weekly I get that job. Reference dimensions are really important, and sometimes people don't think about this, but you're actually scaling the vibration measurement to the vibration structure. Okay, so it's important so that we calculate the amplitudes of the time waveforms in the spectrum properly. Reference accelerometer measurements should be used to collect the X, Y, and Z responses at a normal route measurement location. And I got a couple things. If I'm taking measurement, I need some type of reference. The diameter of this motor bell housing was 19 inches, so that was my first shot at that. This is the motor stator measurement, and it started on the motor inboard side and went to the end bell. and we can pick our distance that way. It was 21 inches for this application. So we have an axial measurement across the bell housing, and we have lateral or vertical measurement across the length of the stator and the motor. I also took some measurements of the nameplate, and it was 5 7/16 inches, so I could select points across there to be a little more precise to the area where I was taking data. And probably the best way to do this is to measure your transducer. So we did that. This is 3 7/16 from the connector to the magnet. And the idea behind this is we put this on the motor housing, like I showed here. We can take an actual measurement from the magnet to the connector, and we know what that exact value is. So we're scaling our data with our transducer that we're getting a reference for. So kind of circular logic, but it works out really well. This is how I set up the first experiment, and it was just one of the cooling towers. 32.3 is the first one we looked at. I'm looking at a displacement plot here at running speed and a velocity plot at running speed. So same data, just one is differentiated or integrated from the other. Okay, I have my spectrum that I loaded from my accelerometer as I took data on each machine. This is the machine is 32-3 X, Y, and Z. So I can put my cursor on 1787, which is the turning speed of the motor, and I have a vibration level. Okay, I don't care for the displacement all that much because it's a function of frequency, so it doesn't give me a good severity factor. If I integrate that or differentiate the displacement to velocity at the same speed, I'm now getting a good severity factor. So whatever this is, all I have to remember is if it goes above 0.3 inches per second, then there's some issue developing. Okay, so here's a 0.03 inches per second and 0.1 inches per second. This was in the X and Y direction on the interface between the magnet and the bearing housing. So over here, I got 0.043 and 0.072. So pretty close. You know, we're not in this to get exact numbers. I'm sure I could do better if I spent an infinite amount of time, but that's good enough for getting appropriate levels, and we can go and see how the machine is moving. So now I've tailored the response to an actual piece of data, an actual piece of vibration data. A couple of things we found in the process. Of course, you have to remove the background vibration. So this is the motor. I'm looking down axially toward the cooling tower. This is my magnet and transducer and cable. Okay, so I put a couple of points that I've labeled off of this accelerometer, and you got to be careful here too because it's basically just a shiny surface. So I was trying to get my selected point right in the interface between the transducer and the magnet so that it'll see that color change or that black and white change that's showing motion and get a better calculation of the response. But the background was still going. So this is a pretty high level of vibration back here. A couple things that generated it, the wind going through the wind tunnel effect between the towers, but also the blade pass frequency. So this shaft extends all the way through the middle of that cowling, has a big fan in there, and it's a, I don't know, 2-3 inches from the sidewalls, these fiberglass walls, and it pulses that entire fan stack at blade pass frequency. I took that raw video just to show, yeah, there's motion in the motor and so forth, but there's also motion around it that we're going to have to get rid of. Okay, and the way we do that in the MEscope ODS videos is we take an area, light up all the area around the background. So we have this drawing tool that we put in here. It grabs all the points in the background, it does a calculation to find the average vibration, and then it separates that. It takes it away from both the background and the foreground, and what you're left with is whatever the machine motion is producing. And it turns out it works really well. You can see this a little better by looking at the raw video with the color contours on, and get an assessment of how much real vibration is there. The scaling here, if it gets red like it is on these cracks, excuse me, on the cracks, 0.8 inches per second, which is a very high value. If we think about it, and 0.3 is a worrisome alarm level, then 0.8 inches per second is 3 times higher than that. Okay, why is it showing up only in the cracks? The reason for that is because these are flat areas. These cracks have some deformation to them, so that it's not basically a shiny reflective surface. Here we have very few little spots of color because it can't detect in the direction that it's selecting. It can see vertical and horizontal if there's some type of line or discontinuity there, like you're seeing between all these ribs in the tower you see over here. But regardless, it's pretty high vibration in here. Okay, so what we're going to do is remove the vibration in the background. And we've done that here. We've taken the vibration in the background out. What we're left with is the X and Y location that I have between my magnet and the transducer, and then between the cable and the transducer. And I get kind of different numbers. I get 0.07 in the Y, 0.06 and 0.014. So there's a little bit different in the X direction. In this case, X is in the transducer direction and Y is in the vertical direction. Okay. Now, the interesting thing is when you put the color contour on, and that's what we're showing here. Here's my transducer, and it's in a green area, which is down here somewhere. Okay, 0.07, something like that. I'm getting 0.06. I'm getting 0.06 over here in the other direction. But over here, I'm getting 0.5 inches per second. Well, where did 0.5 come from? 0.5 was the 0.85 a couple of minutes ago. That was the average background vibration that got separated out. So it took it down about 30%, 30 to 40%, and now our highest levels are 0.535. So that's big for here. But this isn't what we're measuring for. So the end bell of the motor is going to be a lot more flexible than the stator housing. So we got some rigid body motion here and some probably ovalization of the end bell on the motor. Okay, and same thing with this bolted on electrical box. It'll move around a little bit as well. But what we're normally route-based trying to discover is not natural frequencies in the end bell or problems with the connector box. We're looking for a transmission path to the bearing. So the bearing defect frequencies are one of the big flaws that we're looking for in walk-around route-based vibration analysis. In this case, it turns out it's not the best place for visually looking at the vibration. Okay, but it's interesting nonetheless. You know, your machine can take a lot of vibration. It shakes in areas that you've never seen before. So the motion is a lot more important than exactly what the amplitude level is of the transducer that you put on there. Did something else, decided to take the background out, which is the one that we just saw moments ago, at 0.535 inches per second. So I have the hot spots here and on the electrical box, and the background standing still. And then I did the opposite. I did the foreground vibration remove. So I took the machine and basically turned it off, so it's not running, but the background was left intact, which you're seeing over an inch per second of vibration back here. Okay. And I did this for all 8 motors, and they'll all kick on one at a time here as they get going. And that's where this table came from. So this was the close-up cell phone X, Y, and Z. And I had a couple columns here, and it looked very much, it tracked really well. There's a couple little outliers, but a lot better than I expected it to. What we're looking for now, once we say, yeah, this is a pretty good estimate of the alarm levels, and we're probably okay, the video is doing a good job. Now we look at the motion and try to see what we can see. And if we can trust the amplitude level from a close-up, any other direction should work out the same way. And now we can see the entire structure. As long as we scale it properly, we can judge the amount of defect in it. And you can't see it, you might be able to feel it, the vibrations that are causing a looseness or a misalignment or a broken weld or what have you, foundation problem. But this is the way to provide amplification to see it, rescaling the amplitudes and pulling out the meaningful data from the video analysis. This is the 8 channels of the cell phone video for the whole machine, and they'll all start shaking in a minute here, kicking in. So if you take a minute to look at these and look at the piping and support structure under the motor, there's some twisting value there, and I think it's torsional in the motor. So we got some vibration. This one's a little stronger. None of them are above what would you'd consider an alarm level, but regardless, there's some fundamental motion here that some of them have and most of them have, but it's slightly different variations. Okay. I also took some data on here and compared it back to my accelerometer data. Remember, I told you those flat spots on the cowling here are perpendicular to the camera, so they're not going to pick up the XY motion, and you don't have a whole lot of changes. But these discontinuities where the shadows are, that's where the vibration is going to show up. It's the same sort of problem we have here. I tried to pick a spot, and I ended up picking a bunch of them on another view, but where the transducer is, at least 2 of them on the transducer and then another one in here next to it, but this was too flat. This wasn't giving me good results. But regardless, you can start finding out how to best handle the situation. If you do want to get a little more into this and get a little more precise, put a transducer on there, take your measurement, and then take a video and leave the transducer there. And now you can directly compare the location with the amplitude for the video and scale accordingly. And a couple pictures, just like I started before with the other camera and the close-up view. I have a displacement plot showing the X and Z directions, and I have a velocity plot. I differentiated the data, it's push of a button on the fly type stuff. And now I have X and Z type vibration, okay? Over here, this value, 0.215 inches per second, is 0.195. So very close, 0.07. Over here, it's 0.07. So very good, I don't know, accuracy, I guess, the closeness to a known value. Good accuracy in this, and I've already changed it in the close-up view. This is the view, the overall view in the horizontal direction, and this was 32.3. This is also 32.3 and data in the axial direction. Now this one doesn't match. If I go here to my velocity, I have 0.25. Can't read it. 0.52, and I have 0.43. Here I have 0.405 and I have 0.07. Those are way off. The problem is I'm measuring on the end bell. Remember how the end bell kind of lit up on the top up here? It's much higher vibration here than it is back where the accelerometer is. And I took too much of a straight on view. I should have taken another 30 degrees or something so I could see the transducer a little bit better. but that's how testing turns out sometimes. This is same one, motor 32-3. It's the first one on the list. And you can see some of the background vibration. So what I did was I took out the foreground. So meaning I took out the vibration from the motor, the support structure and all that, this cross beam that was providing support for the structural beam. And we're just looking at the cowling vibration. And some of the vibrations, 7 inches per second, 10 inches per second. There's vibration in the cowling along these slot lines that you saw in shadow form before. There's also a cable running down here that is, I'm not sure what it is, for lightning strikes or whatever, a grounding cable. There's a cable for my transducer running across the floor, and that's swinging a little bit, so you get much higher vibration from a swinging rope or a chain or what have you. This is interesting. This is where the floor vibration is. Over here, you can see it from the accelerometer cables, but on this side, all you're seeing is a crack in the floor, and you can see the change in vibration there. And we're in big, really big numbers. So just to give you an idea of how different the background can be compared to the actual vibration of the machine. My other set of data, this is the horizontal view again, but it is high-speed video in this case, a high-speed close-up of what the overall machine vibration is going to be. So I have 0.15 inches per second in the X, and I have 0.08 in the Y. 0.15 compares roughly to 0.195, and 0.07 and 0.08 are pretty close. So these are good measurements that I found. I was getting good at it after a while of processing for days, that I'm picking my spots a little bit better so that I get better results. And you could spend a lot of time doing this. I think at this point, I trust the data. And if I have the correct measurement, like the length of the stator or the diameter of the bell housing or the nameplate, the correct dimensions, if I get a good dimensional value for that, I'm going to get good data that's comparable to the accelerometer data. This is the front view with the background taken away, and I have some color contour plots here, so you can kind of see how the machine's ovalizing or whirling a little bit and twisting. And you can see the amplitudes right in here. This was a little oil aerator or something in here that was moving back and forth. So good deal. This was a comparison between the cell phone camera and the high-speed video and how they worked out. And it turned out pretty good for this instance. But I did have some spots that didn't look so good, where I, instead of doing it right at the transducer, I did it in the middle of the flat area that won't allow me to get a good reading usually. One thing I thought about is a cross-hatching pattern. So if I had something I could, on clear tape that I could stick on there, now I would have a reference and I'd be able to see how much that housing is actually moving. So maybe I'll think of that next time. Get some tape that has some design or pattern on it. So I walked through a few of these. This was 34 and 35, 36, 37, 38, 39, and 40, or 10 actually. So I have all the different motors with the close-ups and comparing areas to see if they look similar. This is all of them in a row, so you can see all the high-speed video. You're not going. Oh, shoot. They're not playing. I get out. I can I think I can just get back in. Hold on a sec. It's looped, it's automatic. Okay. This should work now. There it goes. So it gets a little complex with all this data on the screen. So now I can set back all this. I know I have real data. I know it looks pretty good with respect to the, pretty good accuracy with respect to the accelerometers. And now I can see, yep, it's true motion. What's it telling me? And I'm back to the visual again. So in this case, not a whole lot, because I picked 8 machines that were not in alarm. A little bit of bouncing in this one that's a little different from everything else. And over here, a little bouncing as well. But for the most part, they look pretty similar motions. Nothing really exciting, nothing that's in alarm. All right, we have one other aspect of this, and I have my repeatability, I have my accuracy, and we kind of covered those as much as we can. I want to extend that to the quality of the video processing. If our resolution is poor, this is going to affect the time waveform and the frequency spectrum. So we want to make sure that we get right some of the setup parameters right before we go in and start processing data. Okay, and I have a good example of how that works. This is a belt-driven pump. So here's my motor outboard end, belt drive, pump. And this is for fly ash. They spray pump, they call it. They spray all the fly ash, get it wet, and it clumps together, and you got a bunch of mud that you can get a little bobcat in and get it, dump it all out, scoop it up, and get it out of there. But what we're going to do is something I did in an earlier seminar or webinar. I was interested in how this develops, how big of a clip you need for your analysis, and what's a good guideline. So I took a 0.05 second clip of data, 0.05 seconds, the time waveform looks awful. The frequency spectrum is just blocky. The animation doesn't look, it's doing something, it's trying to, but with resolution at 1200 CPM per line or 20 Hertz per line, it's clumping a lot of things together. So it's not giving me an accurate representation of the time waveform, the spectrum, or the animation. So same sort of idea, except I kept changing the amplitude a little bit. So 1/10 of a second. Let me get those going again. So I took 1/10 of a second, minor improvements. It's still 600 CPM per line of resolution. So I have more, I'm clumping peaks that are of interest to me together. And I want to separate those peaks in the time waveform and in the spectrum. So 1/4 of a second, waveform is starting to look like something. I'm starting to get peaks in there, but there's so much noise you can't tell what's good and what's bad. 0.5 seconds, starting to look a little better, starting to clean up here. This is clue you in, spoiler alert. This is what I'm looking for, these 4 frequencies right there. Still not too good, 1/2 a second. 1 second of data, I'm getting a clean spectrum and clean animation. And what's different about this one looks a little blocky, a little choppy. These don't have deformation in the deck the way this one does. So this one, you can see the deformation. This one, the deck's flat. It doesn't look like it's distorting. This one's getting to the point where it is distorting. And that's actually part of the natural frequency in the motor platform. So we go back, we have 1 second through 8 seconds. So at 1 second, I have a pretty decent looking response. Still 60 CPM per line. I'm a little tight on picking out some of these peaks. 1.5 seconds, 40 CPM per line. 2 seconds, we start dropping the noise floor and accentuating all these peaks in here, okay? And we're at a certain level. when I do a lot of my analysis, I set my F max to 500 hertz, and I use 800 lines of resolution, and that tends to be a good enough screen to be able to pick out individual peaks and not take forever to do. So I've kind of always done that, and it turns out 2 seconds of data is a little better resolution than that, 30 instead of 37 CPM per line. So this is probably the magic location. I did a couple extra. I did 4 seconds of data and 8 seconds of data. And in the software, it's looking through every frame. And if there's 1,000 frames per second, this is a little over 8,000 frames that it has to look through. And that's I have a gaming computer that's very fast, and that'll take maybe 12 minutes to do for each animation I want. For 8 seconds, that's not worth it for me to get a little bit better noise floor. At 2 seconds, it's going to take me 2.5, 3 minutes at tops to generate a spectrum and a waveform for all those frames. Instead of 8,000 frames, I now have 2,000 frames. Okay, so it's a big deal. Sitting around and waiting for a very marginal gain is a problem for me. The other thing that we're working on at Vibrant is ODS-FRF. So the ODS here, or the discrete Fourier transform that we get, is fantastic. It has, you can put your cursor on any peak, get the phase values, get the animation results you want, and it works really well. Okay, 2 seconds is probably the key feature in this. For the ODS-FRF, we're not limited to that. We can average and overlap process the signals and clean up the noise floor. So it might be that we could do the data a little bit faster, but we're still working on that. That's probably going to be in the next month's webinar. Pretty exciting signal processing stuff, though. Now, I get all that put together, and this is what I want to get to. I want to be able to see faults in this detail that aren't all choppy and blocky. This is a nice, clean animation. It's 4 different frequencies. 2 of them are, well, they all might be natural frequencies, but 2 of them, one of them's 719 RPM is the pump speed, 1768 is the motor speed, and then these are 2 natural frequencies that probably line up with some belt frequencies that are giving us a response. Regardless, they're all highly active operating shapes. What can make them better? A normal exposure, we've already looked at that. We can add contour colors to it to see the degree of flexing, the degree of vibration a little bit better. We can add orbits, and this is going to give us a directionality feature. It looks more like it's bouncing straight up and down. There's a little bit of off-axis motion. Over here, the vectors are showing us basically a time waveform visualization of the moving structure. This is the same sort of plots for the motor speed. So at motor speed, our animation's identical. It's just how we view it, with color, with orbits, with vectors that are giving us a little story, okay, on how that machine's deforming. Okay, it is 10 minutes till 2 in my part of the world. I got one more thing to talk about, unless you want to do this, Mark. I don't know if this is the upgraded sheet yet, but we have training, we have good camera packages, and we have also, ODS videos, the product, which is phenomenal and getting better every day. Training, some camera basics, the software overview, lighting and setup tips, best practices. We have generating ODS videos for, it could be I have hundreds of raw video for any class, any training. Once you start getting it, it's just repetition, and you start going. Somebody commented just recently on what are these scripts and hotkeys? They didn't show up in my software. Well, they're not in the final. They're not in the software, the final package, until they get hardwired in. The hotkeys have been. We have an idea. We build that idea and see if it works in the software. Work out the bugs, and then with a hotkey, basically, or a script. And then we install it in the software. And one of the usually every Friday there's a new version of the software coming out. But there's a lot in here, a lot that can be done, and it is truly something that you'll see something different every day. What do you think, Mark?
We have a couple questions. Yeah, good stuff, Dan. We got a couple questions that come in. If you got some questions, go ahead and get those typed in. Into the dialog box. The first question, more of a comment. Can you talk a little bit about the mag phase display? You had some of those images back there. Yeah, it just bounced back and.
Yeah, the mag phase display is just it tells you for a given point. I think this one's not the greatest. It's something like this. So. Usually my transducer is going to be somewhere right here on either side, and for detecting bearing faults. We can pull up labels on the point that I select to do that's closest to where the transducer was measuring, and it'll give me a location, what direction it is, and what the amplitude level is, and then it'll give me a little phase difference between that and a reference point. In this case, it's just showing me its own reference, which is about 90 degrees. But if I assign it to another point and say, what's the phase difference from here to here, it'll tell me they're in phase or they're out of phase. It's just a quick look, kind of like a bubble chart when you're doing just a manual phase analysis.
Great. Next question, are all images unfiltered motion or filtered to the running speed, 1787 CPM?
ODS videos is different. It isn't one peak at a time. Once we process it, and we use 2 seconds because that's a good balance between speed and resolution and so forth, that 2 to 3 minutes that it takes to generate that, it generates the entire spectrum. So you don't have to pick another peak and do that process over again. Some of the other vendors can only handle 1 peak at a time. We have the whole spectrum showing up at a time. And I mentioned the ODS-FRF. These are just discrete Fourier transforms. So you can't do any signal processing with them unless you turn them into operating deflection shapes or ODS-FRFs. And then you can do a lot more averaging and different things to reduce the noise floor. Next.
Can you see, let's see here, let me make sure I'm on the right one. Can you see looseness between motor and base using phase derivated from your image?
Oh yeah, sure. That's one of the best things for it. All the problems that develop in vibration analysis that are phase related are unbalance, eccentricity, misalignment, looseness, bent shaft, cocked bearings, and I think I said looseness already, but mechanical looseness type A is a loose bolt or a broken flange or what have you, a weld cracked, and you can see relative motion. In fact, I don't have it with me. I had a motor pedestal that was cracked, and I just took a quick video and you could see the crack opening up. You couldn't feel it. You couldn't feel any pinch, but under, with the software enhancement, you could see the crack moving. So we could tell it was still propagating. But yeah, all those things are phase-related problems, especially foundations. A lot of my work is finding foundation problems, and this is a great tool for that. And it's a first look. it might not be the last thing you do. It might be the starting point. You go do some analysis, you take a few pictures, you get all the feet on the motor, you take all the feet on the pump, and you go back and look at it and say, oh, there looks like there's something there. Then go do a normal ODS, or not a normal, a traditional ODS analysis with accelerometers. Now you can really get a precise look at what's going on in the machine.
All right, next question just popped in. Is it possible in the software to carry out measurements on different planes?
Different planes. Not sure what you're referring to. Probably, can you do two directions at the same time? You can with a synced camera, and they at Kronos, where that's where we get our high-speed cameras. They're working on that all the time. So they have some systems they can set up. A little pricey probably to synchronize the cameras, but actually no, there is a way in the software right now to synchronize them. But I didn't have any of the. I don't have two cameras to spare with cabling and all that. So I'd love to see how that's done though, if you're going to do it.
Yeah, that would be pretty cool. Next question: how long does it take to set up your equipment to take a group of images? Good question.
Not real long. Making sure everything's charged up, getting the lighting right, that's probably the biggest thing. The high-speed camera, the cell phone, not so much. The cell phone will really do a great job under any light condition. The high-speed camera gives you a higher frequency range, but it's a real light hog. It really requires a lot of light. So it looks for, if you can zoom in and get multiple panels on the object of interest, that'll help a lot. I just listed off all the phase-related problems. The cell phone frequency range, the frames per second, giving you an F max of about 120, that's going to capture most of those phase-related problems. Looseness, misalignment, bent shafts, cock bearings, unbalance, and so forth. Oh well.
Good question. Dan, I had a question. I assume you used the same tripod for both cameras. Did you just swap them out?
Yeah, there's a little attachment for my cell phone. And I just use that. It's like a spring-loaded thing for putting on your dashboard. I screw it into my into a tripod, and it works pretty well.
And since this was an outdoors, you didn't have to add any additional lighting. You didn't have your light bars.
No, but you can see how blue this is.
Yeah.
Look at the blue tint here is because of the that's the wavelength of light that it's closer to. The ultraviolet end, and it the LEDs react to that inside the camera. Not the LEDs, the sensor in the camera reacts to that end of the spectrum.
Yeah. Great. Well, that is all the questions we have for now. If you have some additional questions that maybe will come up later on, you can always go ahead and email us. You can reach Dan at modalguy@aol.com. Or if you have some additional questions or sales-related questions, you can reach us at sales@vibetech.com, and we can go ahead and get those questions answered for you. Again, we are recording this, so we'll get this posted up on our YouTube page here, probably Monday, I'm guessing at the earliest. And feel free, if you got any additional questions, reach out to us. And stay tuned. We'll get another one of these spun up here next month, and we'll fire out an email to everybody giving you a date and time. Any last comments, Dan?
No, I think next time we'll probably do something on ODS-FRF and show you how to average and overlap process your data from your videos. It should be pretty interesting.
Very good. Well, I hope everybody enjoys the rest of your summer. We got a couple weeks left here, and stay safe, and we will talk to everybody soon. Take care.